Hello friends, welcome to this session. In this session, we will discuss on shear stress distribution for various types of the sections. So, in the earlier video lecture, we have studied the derivation of shear stress formula. So, in this video lecture, we will study the what are the different various sections are available and what will be the shear stress distribution of these sections. Let us see. In this particular slide, there is a shear stress distribution for various cross sections. So first cross section is rectangular section. The shape of this cross section is rectangle. That's why it is called as a rectangular section. So you can see we are just showing that there is a distribution. What will be the distribution of the shear stress when the shape of the section is changes? For a rectangular section, you can see suppose there is a depth D is there and breadth B for rectangle. At that time, the diagram and the right hand side you can see the shear stress distribution or diagram for the shear stress. So from the diagram you can understand that at the center there is a maximum shear. So symbol for the shear stress is tau. Tau max is the maximum shear stress. Tau max is the maximum shear stress. So from the figure you can understand that at the center, at the neutral axis, there is a maximum shear stress is exist. Maximum shear stress is exist. And at the end, at the extreme end, there is a zero shear stress. Okay. So as the distance from the neutral axis increases, the shear stress is decreases. Okay. As the distance from the neutral axis increases, the shear stress is decreases. And at maximum distance, at maximum y, from the neutral axis, there is a shear stress is 0. And at the neutral axis, there is a maximum shear stress. So now you can see here for this rectangular section, the tau average. Tau average is the average shear stress. So there are actually two parts. One is the maximum shear stress and another is the average shear stress of the section above the neutral axis. So we should have remember from the examination point of view that what is the maximum shear stress for the rectangular section, what is the average shear stress for the rectangular sections. If you they ask about the section is given and they are simply asking that what is the maximum shear stress, what is the average shear stress. So in this particular slide, so there is average shear stress for rectangular section is, you can see here, that is force, shear force divided by the area. So now you have to remember that shear stress is nothing but the shear force divided by the area or cross section area of the section. So tau average, you can directly write that force divided by what is the cross section area of rectangle. Area of rectangle is D into B or B into D. So force divided by area is BD. So that F divided by BD is the average shear stress. And what is the maximum shear stress? So maximum shear stress, that value is directly it is written. So this is 1.5 force divided by BD. Okay. Or this or 3 by 2 F divided by BD. So this value, this is the tau max value. You have to remember this 1.5 force divided by BD is the value of tau max. That is the maximum shear stress. Below you can see there is a circular section. For the circular section, this is a diagram. It is similar diagram as the rectangular section. Tau max is maximum at the center at neutral axis. So the value of tau average is same, that force divided by area. So you can see here at the bottom there is a force, shear force divided by what is the area of the circular section. Area of the circular section is pi by 4 into d square. We can easily determine the area of circular section. So that's why force divided by area, force divided by pi by 4 into d square. So this is the average shear stress for the circular section. And if you talk about the maximum shear stress, so tau max is equal to 4 by 3 tau average. So we already knows that tau average. So if you multiply by 4 by 3 means 1.33, you will get the tau max value. So we have to remember this average tau and maximum tau. Okay, tau max and tau average. Next, shear stress distribution again for triangular section. So for triangular section, the shear stress distribution you can see here. There is a tau max is equal to, actually in the triangular section, the neutral axis, you can see there is a, what is the position of the neutral axis. It is a capital H, sorry, small h is the height of the triangle, and neutral axis or centroidal, it is exists at 2h/3 from the apex or top of the triangle. So already you know that this is a 2h/3, and from the bottom if you say only h/3, and center is h/2. Okay, so tau max is equal to 3/2 tau average. So tau max is exists at the center at h/2. So you can see here. So now tau at the neutral axis. So neutral axis is there at the, from the apex it is 2h/3. So neutral axis is from the apex, if you see the distance, 2h/3. So what is the tau? So it is the, yes, so 2h/3 at the neutral axis. We can determine the tau, it is 8f divided by 3bh. So this is the formula of tau from the 2h/3 from the top. So 4/3, we know that force divided by area. See this F, force divided by area, and if you solve this like this, so 1.33 into tau average. So this is a formulas are there actually, and from this you can see, suppose here the tau max is equal to 3f divided by bh. So this is the formula for 3f divided by bh is the tau max. So if you divide these two parts, 3/2 separate and f upon area, because we know that f upon area is the tau average. Tau average is the force divided by cross sectional area. Okay, so if you put that f upon area, what is the area of the triangular section? You know that area of the triangular section, all of you are knowing that area of the triangle, 1/2, we can say that 1/2 into base into height. So that area we can determine. If you know the base, if you know the height, you can determine the area of the cross section. So now, so that this 3/2 into force divided by area, if you put, so we will get the tau average 1.5 tau average. Okay, so this is a value 1.5 tau average for the triangular section. So here it is a tau average, tau max, and tau at the neutral axis, it is determined. It is here the formula. So at the neutral axis, the tau is 8f/3bh, 8f/3bh, or in terms of the tau average, 1.33 into tau average. So this is the tau shear stress for various locations. So in the bottom you can see there is a hollow circular section. Hollow, you can see this, there are two types of the circular section. One is the hollow, another is the solid. So out of this it is a hollow circular section. So the neutral axis is there, but there is a changes in the shear stress distribution or diagram. So shear stress diagram is like this for the hollow section. Okay, so obviously there is a maximum shear stress exists at the center at the neutral axis, tau max. Okay, so only just you have to remember that what is the value of tau max, tau average, and where it is the maximum shear stress and the tau average and the zero shear stress are located. So again, in this particular figure you can see there is a hollow rectangular section. The shear stress is, the diagram is like this. The diagram for the hollow shear stress is like this. You can see here is a maximum shear stress is exists at the center at the neutral axis and zero at the extreme ends. So always there is a zero stress at the extreme ends, because whenever from the neutral axis the distance is increases, the shear stress decreases. So in the I section again you can see I section. So there is a one formula, the derivation is already available of this tau max for the I section. If the capital D is the total depth small d is the depth of web, thickness of the web is small b, and d by 2 distance from the neutral axis. If it is there, so tau max can be determined by, or this is already derived, this particular expression is derived from the derivation. So, but for the competitive examination, many of the times they directly ask that what is the tau max. Okay, so in that case you should remember the formulas. So from this we can determine the shear stress, maximum shear stress. So F upon IB, B upon 8. So here it is capital B is the breadth, capital B is the breadth of flange, small b is the breadth of web. So there are two parts, one is the web and there are flanges. There is a top flange and there is a bottom flange. So B by 8 multiplied by d square minus small d square. In the figure you can see capital D is what, small d is where it is there, plus BD square divided by 8. So this is a formula to determine the maximum shear stress or tau max for the I section. So symmetrical I section is there. So tau max can be determined by using this formula. So again the shear stress distribution for other section, C section is there suppose. So already you know that at the center there is a maximum shear stress, and this is a plus section. It is called as the sign is plus, section is plus, that's why it is called as a plus section. But you can see what is the changes in the shear stress distribution. Okay, so obviously at the top there is a 0, bottom also 0, and where it is the maximum shear stress located. Okay, maximum. Okay, so this is the shear stress distribution for plus section. This is a distribution for C section. So you have to remember because many of the times in the objective type of the questions that diagram they also shows, and they are just asking that which diagram is correct for that section. Okay, so you should remember the diagram. Okay, where it is a maximum, where it is a 0, and what is the shape of the shear stress distribution. And now this is a shear force distribution for other section like a H. Shape of the section is H, that's why it is a H section. Actually it is a I, but it is in the horizontal direction, that's why it like a H. So H shape, again the shear distribution diagram is this. And last, it is a T section. The shape of the section is T and the diagram is in front of you. Here it is a tau max. You can see the diagram of the T section is this. Okay, so thank you very much.